I'm here with you with another sessions in homomorphic encryption. So this session I'm going to talk about another very important paper that is called boostrapping. I write the paper and you can see the link anyway in the description of my video, but it's called boostrapping. For approximate homomorphic encryption. So I just call it HL or HE homomorphic encryption. Let's see how that's gonna work. And I try to make it simplified with example instead of focusing on the equations and proofs. Of course, if you're interested in that, would be great, and I highly recommend that you read the paper. But here we're gonna make it simplified, so for those who are more newer to this field, they can understand it. Let's say we have a hospital that is sending some weights to an aggregation server. So here again I make it extremely simplified. So I'm just trying to figure out that the hospital is sending a weight that is equal to 0.45. And there might be other information too. For example, here it can be also W2, W3, W4, but I discard them. Of course, this is the same process. So first of all, we have to scale this weight. So we multiply it by 1000. So that becomes the scaled weight equals to 450. So now it wraps these four integers. Of course, I'm just again showing just one of them into a single polynomial equation curve. And if you remember, that creates mx. Now we need to encrypt this message and we create C0 and C1. Now hospital also choose a boundary that is very big. For example, Q is equals to 1 million. Now hospital uploads or sends C0 and C1 to the cloud server and goes offline. I mean, there's nothing else to do on the hospital side. The server side, if server do decimal scaling factor squares, for example, here we have 1000 goes to 1 million. So this kind of like blow up the numbers. So you see, because of course, if we keep multiplying numbers, that gonna keep increasing, and that's the same problem that I discussed in the previous paper, and that was delta 2 problem. That let's say if your delta like here is 1000, then delta 2 would be 1 million, and then delta 3 would be much bigger, and delta 4 is much more bigger. So in that, for avoiding that, if you remember in the previous paper also I discussed that we have to use a technique that is called rescaling, which means that we have to divide our equations or our polynomial by delta to make sure that it doesn't explode. So the server divide the entire mass, including the modulus boundary here. So for example, if before the multiplications we have modulo Q is 1 million, then after first multiplication that we do, then we have to divide it by 1000. So that means like 1 million divided by 1000. So we get 1000. So see, if we do this for the second time, and then we divide our equation or our polynomial by 1000, so our Q will reach to 1. You cannot even continue more. So this is not good. We shouldn't get to here number 1. So what to do? Let's consider Q to be 1000, and I have to use a technique that is called bootstrapping here, and I'm gonna explain now how it's gonna work. And here actually Q is gonna be 1. It's very small. So what to do? The first phase of this paper is called mod raise or modulus raising. It's very simple. So this is the decryption formula that we discussed in the previous session. So what we are doing, let's say that after we did the first multiplication, t is equals to 3450. And the message that is hidden that I mentioned in the top is 450. So what to do now with that? And q is actually modulus is 1000. This is the old modulus. Sorry, there's been a... Here is our old modulus. So if you remember here, I mentioned that we should choose Q1000. So now the server runs modulus raising and bumping the metadata back to metadata tag to, sorry, some errors here, metadata tag to 1 million. So what I'm doing here is that I reset my queue to be 1 million. Okay, now the server side needs to do the phase 2. Phase 2 is coefficient to slots. It's very simple. Don't get intimidated by this complex formula here. This is basically just we get the current encrypted state, and Z prime here is the, sorry, UK here is the known unencrypted encoding matrix that the server multiplies against the rotated ciphertext. So now Z prime, the whole thing that you need to consider here is that I put this value of the ciphertext, or actually of the hidden message, inside this vector. So you see now 450 comes here. Next, I have to do an evaluation exponential function, or evaluation of complex exponential function, and this is the formula for that. ET is equals to Q divided by 2 pi multiplied by exponential of 2 pi IT. This is I because it's a complex number, and Q. T is your hidden message, Q is your old modulus. So let's put everything into the perspective. And of course also have this in mind that computers cannot calculate an infinite exponential function, and we have to use a two-step pipeline that here is explained about that you can read it, but don't worry about it. I'm going to show it by example, and hopefully that makes things easier. In our example, Q was equals to 1000 and T was equals to 3450. If you write these equations, and this is equals to ET, this equation is equals to 2 pi I, 3450, and 1000 is going to be equal to exponential of 2 pi I, and 3450 is actually 3000 plus 450. And using a standard exponent distribution rules, we can write it this way: exponent of 2 pi I multiplied by 3000 divided by 1000 multiplied by exponent of 2 pi I multiplied by 450 divided by 1000. And this is equals to exponential of 2 pi I multiplied by 3 multiplied by exponential of 2 pi I multiplied by 450 divided by 1000. So this gonna be equals, the first term here gonna be equals to 1. So the result here that we get for updated slot 1 gonna be this exponential here. So I just write, instead of t0, I write this expression here. Now we go to phase 4. Phase 4 is called the extraction of imaginary part. Euler's formula says that any complex exponential is made of two parts. The first part is an cosine, and the second part is an imaginary part. So the server can actually discard the real part and only can keep and isolate the imaginary part. The imaginary part is the sine 2 pi m divided by q. This is the equation, which is equals to this equation on the right side, but don't worry about that. So what is important here is that if you look at this part that we discussed previously, q divided by 2 pi multiplied by sine 2 pi m divided by q is actually equal to m. But there is a condition, and that condition is that m should be very small, much smaller than q. That we'll discuss it later. Now let's substitute our values. Q is 100 and m is 450 and q is 1000. Now if we use our calculator, this is going to be equals to 4980. But interestingly, this failed because the sign of x is not equals to x, or is not actually close to x, when the angle x is very close to 0. Sign of x is actually very close, or approximately is equal to x, when the angle of x is very close to 0. So the server needs to trigger bootstrapping earlier. So we shouldn't wait until q is equals to 1000. Instead, for example, we can do all this calculation when q is equals to 10,000. Because 10,000 is much bigger than 450, but 1000 is not actually much bigger than 450 is not much smaller than 1000. So if we use instead this time q equals to 10,000, so the result gonna be 444.05. Perfect. This is very close to 450. Now we have to figure out what is the updated modulus. So the updated modulus gonna be the old modulus, the one that we updated that now is 1 million. Not the old modulus, actually the old modulus that after we have done all the phases here, divided by all the modulus that consumed during the bootstrapping. So let's assume that q1 is much larger than q. So we successfully could recharge the ciphertext level lifetime. I know it might be confusing, but just let me put it this way. Each time that you try to multiply stuff on the server side, you're gonna explode the equation. To avoid that, we have to use a technique that is called rescaling, which basically means that we have to divide everything by delta. If you keep dividing the modulus q by delta, ultimately you get to a very small number that you cannot divide further. So to avoid this problem, we have to use a technique that is called bootstrapping. And for bootstrapping, we went through all these 4 phases. And actually it's 5 phases. I didn't talk about the last phase because the last phase is again to convert the slots to the coefficients here. And that's the opposite of coefficient to a slot that was phase number 2. Yeah, thanks so much for watching. I know it can be a bit tricky. I just hope that it gives you some ideas and give you motivation for starting to read this paper. And if you have any question, feel free to ask in the chat and then we'll talk more about it. Thanks so much for your attention.